Welcome back to our journey through the world of embedded systems and SPI. In this part, we'll be exploring an example by looking at the Max31855 temperature sensor. First, we'll discuss the datasheet. Later, we'll be using the digital oscilloscope to decode the data on the SPI bus. In our previous video, we laid down the foundational knowledge of SPI, discussing the basic operating procedures and highlighting 4 different modes. We also mentioned the data transmission lines MOSI and MISO. But here's where it gets interesting. If we glance at the figures from the datasheet, you'll notice something peculiar. There's no explicit mention of MISO or MOSI pins. Instead, you'll find pins labeled SO, which stands for Serial Data Output. You'd be surprised to know that this pin serves the same purpose as the MISO pin. This seemingly contradictory information presents a case where slave devices may not require both MISO and MOSI lines. Furthermore, this may be decided if the peripheral devices are read or write only. Now, let's zoom in on figure 2 in the datasheet. Let's take a look at the chip select area, where you'll spot time delay labeled TCSS. This delay indicates the clock phase will be set to logic 1. Next, we need to determine whether the clock idle state is high or low. This crucial piece of information helps us ascertain the clock polarity, which in this case is logic 0. Finally, examining the mode chart to the left, we can determine the mode of the signal is mode 1. Alright folks, now it's time to put the Max31855 temperature sensor to the test and decode the data on the SPI bus. As we noted, according to the datasheet, we should be operating in mode 1. Where the clock is rising and the data is read on the leading edge of the clock pulse. If you're not familiar with the software I'm using to decode the bus, don't worry, I've got you covered. I've made a dedicated video explaining how to set up the bus analyzer tool for the Hantek DSO520P digital scope software. Make sure to check that out for a step-by-step guide. After the software does its magic, we're presented with a hexadecimal value, which we'll need to convert into binary. Once we have the raw data, it's time to consult the datasheet to interpret measurements. And if you look closely, here's where it gets interesting. The first 14 bits of our decoded data contain the temperature of the thermocouple. Bit 31 represents the sign, while bits 30 to 20 provide the temperature in Celsius. Oh, and don't forget about bits 19 and 18. They can be used in case you want a floating point value. Simply put, we don't need to crunch all 32 bits. The most significant 12 bits are all we need to convert the data to decimal. Now let's convert the numbers. If we convert hexadecimal 17 to decimal, we get 23 degrees Celsius, or 73.4 degrees Fahrenheit. And you know what? That sounds pretty reasonable to me. And there you have it, folks. We have successfully decoded SPI from the Max31855 temperature sensor and verified its accuracy. Join us in the next segment as we dive deeper into decoding SPI data and uncover more insights into embedded systems. Until then, stay curious and keep exploring.